Before I show you these new 2 points, let me introduce some new vocabulary. All right, I warned everyone first day of this unit, a lot of new vocab. First one today, median of a triangle, a median. Go ahead, I'll let you read the directions first. All right, the definition, excuse me, of what a median in a triangle is. All right, so go ahead, just quickly read through the definition, and maybe we can put some extra markings on our diagram now. All right, so it's a segment triangle. One end has to be on a vertex. All right, in a median, it has to start at one of the vertices of the triangle. It can't be hanging out on one of the sides. It's got to start at a vertice, and it's drawn to the opposite sides. What? Opposite sides, midpoint. Okay, the opposite sides, midpoint. So if I tell you in this diagram, AD is a median, starting at a vertice, going to a midpoint, you should be able to tell me something out now. One conclusion, at least, if that's a median starting at a vertice to a midpoint. You should be able to tell me one thing up here. Here we go, 29, anything? Because what do you know point D is? That's the midpoint, yep. So BD congruent to DC. Did I say anything in the definition about being perpendicular? No. No. All right. Is this a perpendicular bisector? No, it's not. It's called a median. It only goes to the midpoint. All right. Only goes to the midpoint. And the saying I like to give kids every year to remember what a median does, medians go to midpoints. Medians go to midpoints. Next one, an altitude. Some of you may or may not have heard this, an altitude. You could put in parentheses here. Maybe you've called it the height of the triangle in past math classes. That's what it's usually referred to as, the height. So go ahead, read through the definition quickly and tell me what I can mark on my diagram here. What could I add to my diagram or make a conclusion now if it starts from the vertex and is perpendicular to the opposite side now? Doesn't go to the midpoint, but it's perpendicular to the opposite side. Either tell me a conclusion or tell me what markings I can put up here. 3. What can I put up here? Yep, specifically name an angle that would be a right angle. ADB, and I could also do it on the other side, ADC. So I can say angle ADB and angle ADC are right angles. Does it go to the midpoint? No, it's strictly perpendicular. But it always starts at a vertice, all right? And a lot of first-time questions I get, especially from the honors kids, is, can it ever be the same? Can a median and a altitude ever be the same, act as the same line? And the answer is yes, if the triangle is isosceles or equilateral. Okay, so if you want to remember that little quick fact, if the triangle is isosceles or equilateral, the median and the altitude are the same line segment. All right. Questions about those two new ones here? All right, just to make sure we're solid, identify what CD is acting as in every triangle right now. Okay, I've put some markings in some of them. I put some measurements in. Can you tell me what CD is acting as in all these triangles here? So here's CD here. I'm making a right angle. Give me a good name for CD there. Here you go, 23, a good name for CD. That is an altitude. It starts at a vertice perpendicular to the opposite side. That's an altitude. Nice job. How about B now? What could CD be acting as now? Put little 2-inch marks on there for you. Here you go, 26. What could I call CD? Median, because it's going to a midpoint of D, starting from a vertice. Nice job, median. All right, hopefully I'm not tricking you with C. With 28 degrees, 28 degrees, what is CD acting as? Here you go, 21. Do I know anything here? Answer may not be altitude or median. Just a heads up, may not be. I'm not looking for altitude or median here. It's not a median because I don't know these are congruent, and it's not an altitude because I don't know if it forms a right angle, but I do know it cuts this angle into 28 and 28. It's an angle bisector. And this one usually tricks kids here, what CD is acting as. That is an altitude, yes. Everyone see why, ready? Is it coming from a vertice? Drawn perpendicular to the opposite side? Yeah. Yep. Questions from you guys? Okay, in your group, you got about 2 minutes now to do number 2. All right, you got about 2 minutes to try out number 2. First, read all the directions on top. All right, I gave you a lot of information. Do this. Name 2 angles that are congruent, which have a vertex at C. 2 angles that are congruent. Start us off here. 20. Start us off. Angle. Okay, angle ACE would be congruent to angle BC. Yes, because that's an angle bisector. Can anybody give me 2 line segments that are congruent? Probably from the median. All right, CF being a median, what 2 line segments would be congruent? Here, let's hear from 20 again. Angle, you mean segment? Yep, AF congruent to segment. Got it. All right, because CF is a median. Medians go to midpoints. Midpoints cut segments in half. All right, let's keep this train going. Name 2 line segments that are perpendicular to each other. Probably from the altitude. 16. Got it. Nice job. And finally, name 2 angles that are right angles. You're basing that off of part C. 2 angles that are right angles. Let's go 5. Angle ADC. And what was the other one? Sorry. BD. Yes. I just stopped there for, you could call BDC. I had CDE on my paper. All right. BDC is fine. All right. CDE, CDF, CDE. All right. That's fine. Any questions there on all those? Medians, altitudes. Because now you're going to figure out what's so special about all 3 medians when they intersect in a triangle. If you haven't done so already, go ahead and graph triangle ABC for me. Okay, to make this go quick, I'm going to assign different groups just like I did last week. All right, midpoint of AC. Can you, 2 groups right here, find me midpoint of AC. All right, and call it point E for me. Midpoint of BC. Give me these 3 groups right here. These 3 groups in the back here. Give me midpoint of BC and call it point F. The other 3 groups that are remaining, please do the midpoint of AB and call it point G. Sorry. The BC group probably has it the easiest. All right, first two groups, midpoint of AC. What do we have? 5, 5. I got 5, 5. Okay, 5, 5 it is. Everyone go ahead right now. Graph 5, 5. Call it point E. And what I'd like you to do is to draw in median BE for me. All right, if you have a straight edge around, fine. Draw it in as best you can. Median BE. We're drawing in all the medians now. So draw in median BE. You guys I assigned to BC. Hopefully you did that one pretty quick. Midpoint of BC. 8, 4. Everyone go ahead and graph it. And then with the straight edge, draw in median AF. And finally, the groups I assigned to AB. What do you have for point G? 5, 3. Everyone graph it and draw in median CG. And I'm hoping you see something that's been kind of consistent with the in-center and circumcenter. And what do you guys notice about the medians of a triangle? I try to use our big words here. Don't tell me they all intersect at a point. We had a term for that. Look back if you need to. We had a term for 3 or more lines intersecting at a point. Sinead, what do you know about them? They're concurrent. There we go. The 3 medians of a triangle are concurrent at a point of concurrency called the centroid. Yes, centroid. That is the point of concurrency for all 3. What did we just make here? What are all these green lines for me up here? For all 3 medians. Got it. Woo! A third point, huh? To go with circumcenter and in-center. And just like in-center and circumcenter, we should know something about this point. All right? A theorem about that. It's not equidistant from the vertices. It's not equidistant from the sides. This one's a pretty special one. Ready? Centroid breaks the median segment into a ratio of 2 to 1. Here's what I mean. The 2 part, that's from vertex to median. Or centroid, excuse me, vertex to centroid. And I'll show you what I mean on the diagram in a second. The 2 part is the distance from the vertex to the centroid. The 1 part, centroid to 2. What's the other point at the end there? Midpoint. Go back to your graph right now. I don't know. What do we want to call this point? Can't call it C for centroid because I already got C. Z, you got it. We'll call it Z. Here's what this means, everybody. Somebody pick one median right now in our diagram. Pick one median off. AF. All right, everyone ready? If I'm talking about median AF, the part from A to Z, ready? The part from A to Z is double the length of Z to F. That's what this 2 to 1 means. From vertex to the centroid is double centroid to the midpoint. All right, so name another median in this diagram for me. CG. So that tells me C to Z is twice the length of Z to G. All right, that's what this centroid theorem is saying. Breaks the median into 2 to 1. All right, one part is double the other part. Put it to use right now. Here you go. Let's put it to use. Ready? Here we go. M's the centroid. Ding, 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 centroid. So ready? So let's get in the habit. Centroid, I'm thinking two things. How's that M formed? These are all what here? These are all medians. Got it. And what's the special fact about the centroid? It breaks every median up into a ratio of 2 to 1. 2 to 1. All right. So in part A here, WM is a length of 16. What's got to be WX? The entire thing now. All right. Whoa, whoa, whoa. Before we start spouting off here. This part, is this the 2 or the 1 part? 2, because it's vertex, the centroid. So this part is double XM. So if that's 16, what's the length of XM? Got to be 8. And I'm looking for WX, which is the full median. So that'll be, yep, we were correct. Many of us at the beginning, 24. Questions there? All right, one more on this diagram. WM, 12. Find the length of YO and MO. Well, let's start with MO. The part I gave you, the YM, is that the 2 or the 1 part? It's the 1 part because it's from centroid to midpoint. So what's the length of MO? If that's the 1 part and I'm looking for the 2 part, that should be 24, double it. For a total length of, for YO, 36. Ask away. Anything. All right, go ahead for 5 now. I have a question for 5. As you read through it, I do not mention the word centroid at all. But how do you know point G has to be the centroid? Because it's telling you AD, BE, and CF are all medians, and we just found out they all intersect at the centroid, all right, which has to be point G. So I may not come out and say centroid, but at least I gave you enough to figure out that it is the centroid. All right, BG, 2 plus 10. GE, 3x minus 1. They're not equal to each other. They are not equal to each other. I'll set them equal, but I need you to adjust my equation to make it correct. This is incorrect. They are not equal to each other. I need your help making it correct, though. You know, it breaks it up in a ratio of 2 to 1. 2 things I could do here. I could use 1/2 or I could use 2, but it's got to be on the appropriate side. What do you got, Teddy? Yep. Yep, I could do multiply the 3x minus 1 times 2. Because this is equal to double 3x minus 1. Or what could I put with the 2x plus 10? 1/2, and left 3x minus 1 the way it is. Everyone all right why I'm putting the 2 there? Because if you put it here, you're saying this here, I got to do 2 times that to equal GE, and that's not correct because GE is the smaller one. All right, and then from here, hopefully it's not a big deal. 6x minus 2. I'll move the 2x over and get 4. Move that negative 2 over and get 12. So x should equal 3 no matter how you solved it, but that's not what I'm looking for. I'm looking for BE. I got to go back and plug it in. 2 times 3 plus 10 plus 3 times 3 minus 1. And what are we looking at for the length of BE? 24 units. Anything else? How do we feel? We got three. What are the 3 points of concurrency here? Let's review all 3 before I get to the 4th and final one. Circumcenter. I'm not going to go over, we'll go over it a ton what you should know about it, but circumcenter, in center, and then we just found the centroid. All right, quick fact again about the centroid. Some of you may be back in the day when we had a lot more time and we weren't crunched with the Regents exam, we'd actually would construct the median on a sheet of paper. All right, we would construct the centroid and we'd cut it out. The centroid is also known as the center of gravity for a triangle. So if you found the centroid using constructions and cut out your triangle, put your pencil tip, a sharp pencil tip, right where the centroid should be, it would balance perfectly, that triangular piece of paper, because it's the center of gravity. Move it a little bit to the left or right, it would fall off your pencil tip. All right, but it's also referred to as the center of gravity. All right. And ready for the 4th and final one. You will see that I do not spend as much time on this one as I did with the other 3, because it's not that cool. All right, and I'll show you why. It's called the orthocenter. Orthocenter. That is the point of concurrency for all 3. What was the other vocabulary term I showed you today other than median? Altitudes. That is where all 3 altitudes intersect. And the reason I don't spend much time with it is because there's not a special fact associated with it. Like it's not equidistant from the vertices, the sides. It's not, doesn't break it up into a ratio of 2 to 1. It's just there. Okay, it's just there. All right. I do need you to know how it's found by the 3 altitudes, and this is how we're going to finish class today: is where is it located depending on the type of triangle I have. All right, where would the orthocenter be located? Because it's not always inside. It is not always inside the triangle. Let's first start with an acute triangle. Okay, an acute triangle, which I have right here. If you think about an acute triangle, and if I drew all the altitudes in, all the altitudes, does everyone agree, would be located inside the triangle? If I drew in all 3 altitudes, no chance I'd be able to get one that's not inside. All 3, that's awful. All 3 would be located inside. Maybe I could do this. Okay, I'm giving up soon. There we go. Would be located, so the orthocenter inside. But that is not always the case. Let's go to my second type of triangle, which is the orthocenter will not be located in a right triangle. Here's why. How's the orthocenter form? That's where the what intersect? Altitudes. If you take a right triangle, and I probably should have mentioned this before earlier in class, but if you take a right triangle, aren't 2 of the legs altitudes? Everyone agree? Because remember, definition of an altitude, from a vertice perpendicular to the opposite side. Everyone agree? So this is an altitude right here, one leg, and the other horizontal leg is also an altitude. Do you see where they meet? So if I did the altitude for the hypotenuse, guess where they would meet? So it's not inside, it's not outside, it's on the right triangle, yeah. And you might want to get more specific here. Where the 2, I always put where the 2 legs meet. All right, because the 2 legs of a right triangle are also altitudes. And then we've come to our final one, which is an obtuse triangle. Here's the problem. An altitude starts at a vertice, right, and is perpendicular to the opposite side. Is that going to be perpendicular? Nope. Let me try another line. Is that perpendicular? That's not going to form a right angle. There's no way I'm getting a line inside that's perpendicular. So the only line I can get that's going to be perpendicular would have to be drawn outside. All right, in an obtuse triangle, one of the vertices is on the outside, which means what about my orthocenter? It also has to be located on the outside of the triangle. So it all depends on what type of triangle you have to where it's going to be. Okay?